My name is John Archer. I'm a research scientist working here at EPA's Durham, North Carolina research facility, otherwise known as Research Triangle Park, North Carolina. I have a degree in environmental science and engineering, and I'm one of approximately 30 researchers working in EPA's research side with the Homeland Security Research Program. Today I want to tell you a little bit about what we do in the Homeland Security Research Program, as well as I'm going to show you around a couple of our specialized laboratories. The Homeland Security Research Program was established shortly after September 11th, 2001, otherwise known as 9/11, when we had the terrorist attacks on New York City, and then after that some envelopes with white powder were sent to certain locations that contained spores of Bacillus anthracis, which is the agent that causes anthrax. And so EPA, being the lead federal agency for drinking water and protecting wastewater systems, cleaning the environment after contamination events, the Homeland Security Research Program was formed. These acts of terrorism can be with contaminants such as chemical warfare agents, radioactive materials such as in dirty bombs, and biological threat agents that require a scientific research program that's really specialized, with specialized people and training, as well as specialized assets to be able to research those facilities. Our research is very applied and directly assists our customers, who are the response community, the folks that would actually respond to one of these events. So our work has gone on to help following outbreaks of Ebola, following the Fukushima radiological disaster in Japan, following other disasters such as Deepwater Horizon, that would be a chemical contamination spill, and more recently the COVID-19 pandemic. So all of our Homeland Security research conducted here at this facility that uses chemical or biological agents uses what we call surrogates. The surrogates are basically materials that behave similarly to the actual chemical or biological agents but are not harmful. So we utilize those in our research if we have a need to use actual agents for research that's conducted outside of these facilities. So if you would, come on in with me and we'll take a look at a couple of our labs. Welcome, here we are at our fluid modeling facility here in Durham, North Carolina. Behind me, you see a rainfall simulator. The rainfall simulator is one of our tools that we use for our Homeland Security research to be able to study fate and transport of spores that we mentioned earlier, and how they actually wash off surfaces if they're deposited in a wide area event outside. This rainfall simulator is obviously huge, as you can see, hopefully, how tall it is. It's about 27 feet tall. We can simulate rain events less than an inch per hour, all the way up to 4 inches per hour. So we can simulate both subtle rain events as well as simulating an intense rain event, which would be about 4 inches per hour. The important part of this is that we can do rain simulation and simulate wash off from surfaces indoors. We don't have to wait on an event to happen outdoors. And so we simulate that by using what we call coupons. You can see an example of a concrete coupon here. We can simulate asphalt, concrete, or other outdoor surfaces. We would inoculate, deposit spores onto the surface, put it in the rainfall simulator, and then simulate a wash-off, what would actually occur outdoors. Something else that you'll see in here is called a dristometer. This is an instrument that actually measures the rainfall intensity. It actually measures the rainfall droplet size as well. So you can see that inside the rainfall simulator. Up top, you can't really see it, and I'm not going to put the camera inside, but about 27 feet up, we have a nozzle where we generate the rain droplets. When we're generating the rain droplets, we can actually measure here, so we generate a curve. And I think we're going to be able to turn on the rainfall simulator here in just a second so you can see an example of it. What we do is capture the rainfall velocity droplet size with the dristometer. Here is an example of the rainfall right now. So you can see it generates a nice mist. It's actually sweeping out just a little bit. We have to make sure it stays dry. We can also change the size of that, change the intensity to again simulate different rain events. And what we get from that as we move on over is what we call a rainfall curve, or a gun tensor curve. On this computer is a good example of a gun tensor curve that we generate with our rainfall simulator. These curves are actually made during real rainfall events, and so our simulation curve can compare to the actual rainfall curve to see how close we are in our representation. That way we're not just putting the same size droplets down onto a surface. We can actually do the simulation. So really, this is a great example of a Homeland Security tool that is used to study fate and transport of biological material. Here we are again in our same area for our Homeland Security Research Laboratory. Previously in another part of this lab, you saw our commander chamber. Here I want to show you a little bit about a couple of specialized chambers that don't look like a lot other than a big box, but there's a couple of big boxes here that we use to basically look at decontamination of surfaces or separate items that we call coupons inside a chamber, where we can use different sprayers, we can use garden sprayers, we can use pressure washers to look at how these biological materials or spores, or it could be chemical materials, get transported off the surface, as well as how well they get decontaminated. So they don't look like anything special, but we have chambers constructed out of certain materials where we can see through them. We have ports here that actually can utilize a sprayer, and we can hang what we call a coupon inside there. We can contaminate it. We can use certain decontaminants using certain types of sprayers and decontaminate it, and then we can look at the efficacy of that decontamination process. These chambers are also under special ventilation, so it keeps us safe depending on what contaminants that we might use, which are always surrogates, and then the decontaminants, which could be certain chemical chemistries. It could be a bleach-based decontaminant, it could be hydrogen peroxide, or it could be other things. So these small chambers allow us to do research at a bench scale or a pilot scale, so before we take on the expense of doing large field studies, which eventually we will once we get through this type of study. So let's move on over to another area. I want to show you some other equipment for research that is going on right now. You see various types of sprayers here. We currently have a study going on looking at electrostatic sprayers, which are being used quite a bit since the COVID pandemic to disinfect areas, certain surfaces indoors, probably not outdoors, mainly indoor surfaces in healthcare facilities or other facilities across the country. So we're doing evaluations looking at characterization of these types of sprayers, whether they're able to generate a certain efficacy based on the decontamination process. So that's another example of work that we have going on here. Hello again, everybody. Welcome back. Here we are in one of our other Homeland Security research laboratories. This large laboratory is called our aerosol test facility. And behind me, you see our large aerosol wind tunnel. When I say aerosol, I mean essentially a solid or a liquid particle that's suspended in air. So it could be things like fumes, dust, mist. It could be the COVID, SARS-CoV-2 virus particles in air, but anything that's in air that's suspended. And so what you see behind me is our large aerosol wind tunnel. This system was constructed years ago and intended to really test materials and test aerosol transport and aerosol sampling devices for some of EPA's national ambient air quality standards, primarily for what you've probably heard of, PM 2.5, particulate matter 2.5 microns. The interesting thing about this wind tunnel is it's one of the largest wind tunnels in the world. And it's also a recirculated wind tunnel. You can't see it. Right now you're looking at one side of it, but if we get a shot later on, you can see that it's basically a large rectangle. So it recirculates the air. So we can basically move air in this tunnel We can generate particles of different sizes, and it could be an aerosol, it could be a bioaerosol, it could be a spore, anything like that. It could be a chemical particle as well. And what we can do is control the conditions inside the wind tunnel. So we use temperature and humidity control, and we can simulate certain conditions, control those conditions. We can introduce aerosols into the tunnel. And in a couple of our test sections here, this is what we call the human exposure test section. Very large, it's about 4 meters by 4 meters. And what we can do in here is use mannequins to simulate humans that would be exposed to a contaminant, and look at their potential exposure under different conditions to different aerosols. Some of our other special materials that we have here in one of our Homeland Security research labs also look at aerosol transport, also look at aerosol sampling. Behind me here, we have what we call a mechanical foot, where we can actually simulate a human taking a step on a surface and to see what materials might be resuspended based on that human activity. So without having people walk around, we can actually simulate the human foot taking a step under a certain pressure, lifting off the surface, and measure what gets resuspended, whether it's a biological material or what else. These systems you see here are our deposition stacks. So when we want to deposit on a surface, you see the asphalt surface there, we have certain aerosolized devices, or nebulizers we call them, that actually can deposit the aerosolized materials onto the surface, where we can resuspend and measure them, or we can measure what we get on the surface. And this last device here is called our small resuspension wind tunnel. This has been used in previous programs, where we can look on more of a smaller scale of utilizing a way to resuspend materials from surfaces and then capture them on filters. And it's a good way to be able to control it on a smaller scale to see what's happening after materials are deposited and how they get into the air, and how that could be a health effect to humans. Well, thank you again for this time. I appreciate you being able to see some of our Homeland Security research facilities. I hope you've had a good time. I hope you were able to see our facilities a little bit closer and get just a picture of what we do here in EPA Homeland Security Research Program. Hope to see you again soon.
Hello, and welcome to the US EPA's Research Triangle Park, North Carolina campus in Durham, North Carolina. My name is Matthew Pate. I am a mechanical engineer in our facilities operations branch. I also serve as our campus energy and water conservation manager, and I'd like to show you a few elements of our campus around here today. We share a 550-acre, mostly forested campus with the National Institute of Environmental Health Sciences, and our utility plant, which you can't see right now through the forest, but it is hosted by the National Institutes of Health. They serve us an underground chilled water and high temperature hot water utility loop, as well as a pass-through for electricity into our campuses. We're currently standing atop our main entrance plaza for our main administration building and one of our large laboratory buildings. There are actually some classrooms below us. We host a lot of visitors every year, approximately 20,000 visitors for educational events, conferences, expos, and at any given time we usually have about 1,200 federal employees working here and about 1,000 contractors at any time. So when this campus was built, numerous elements of LEED 1.0, Leadership in Energy and Environmental Design, were incorporated as an example to the remainder of the federal government that this example works. This environmental design to save energy, to save water, to be a better and more sustainable facility was put to use as a proof of concept at this facility. When it was completed in 2002, we had the largest rooftop solar array on our National Computer Center at 100 kilowatts. That's since numerous times been surpassed, but it was a great example to start with. The building space here consists of about 1.2 million square feet of laboratory, administrative, office, and computing mixed spaces. So I'd like to take a moment to take you around to a few of the different locations here as a sustainability and building infrastructure effort. During 2014, President Obama issued a presidential memorandum directing all federal agencies to outfit their work sites with pollinator habitats to the maximum extent possible. And this is our first installation on this campus since that issuance of that presidential memorandum. This is our National Computer Center, the front entrance of it. This used to actually be a spoil pile post-construction of the campus. So it sat idle for about 15 years. So this year, and last year and then this year, we've spent a lot of effort cleaning it up, and we intend for this to move forward as a chemical-free pollinator meadow. We're in late October and I still see numerous butterflies interacting with the plants around here. We're mowing a couple of cross pathways, and hopefully in the future maybe a couple of small native trees and benches for people to come out here and eat and relax in the lunch amongst the pollinators. Okay, so we're currently standing in a corridor hallway between our main administration building and one of our laboratory buildings. The atrium actually starts right over here. I'd like to direct your attention to the windows on either side. You can actually see these small squares all the way around. You can actually see the reflection off of some of the building facade. This is a bird film, and it is a one-time permanent installation. We saw an article in a local newspaper where Duke University had applied this exact same technology to the windows of one of the engineering buildings where they were having bird strikes and birds were dying, and they wanted to eliminate that. This actually dropped their bird deaths to 0 immediately, and we applied the same technology here, and we've actually had no known bird deaths since we applied this sticker film to the windows. Before we did this, we actually used to raise and lower a netting on the far side of this window twice a year during bird migration seasons. When birds would try to fly to the lake through the woods over here, they would sometimes run into the window, and this is a human created death, and so we have a responsibility as humans to design our buildings in a way that birds know that buildings are actually here rather than this just being airspace that they can attempt to fly through. So this is a very beneficial, very inexpensive technology which will allow bird deaths to be minimized. If you weren't aware, more than 1 billion birds actually die by flying into buildings in North America alone every single year. So the more that humans can do to minimize these deaths, the better off the bird population will be. We're now standing in an electrical space which contains all of the electrical equipment associated with the photovoltaic solar array on one of our admin buildings. Once the energy is generated on the rooftop, it is high voltage DC. 600 volts DC comes into our building from this array. It comes in as 2 parallel sides, and if we were to install a battery to store that energy for later use, we would do so right here, just downstream of these disconnects. From here, we invert in the inverter to AC, from direct current to alternating current. So it comes out of the inverter as high voltage AC or 480 volts alternating current. And then we transform it in a transformer down to 208 volts or 120 volts for use in the building. Similar to at home, you would use a dryer with the higher of those two, and 120 volts might serve your plug loads, your HVAC loads, and any other lights that you have in your home. What you get from this are some losses. We do not live in an ideal world, so you're going to have electrical losses in the form of sound, which you can hear, vibration losses, which you can feel on the top of the inverter, and heat, which we have an increased temperature in the space as a result of some of those losses. It's about 10 degrees warmer in here than it is in the adjacent people space. From here, these are free for use inside the building. If we were to over-generate, it would charge the battery, and then any excess electricity would go in for the building's use. If we underuse, that battery will never get charged. We'll just consume the battery's electricity and then use the energy that comes in from the roof. Welcome to my favorite solar array on our campus. This is a thin film amorphous silicone photovoltaic solar array. These are flat. They adhere directly to the roof surface. They're literally glued on, each of these strips. Each of these strips is 50 watts. And all of the electrical wiring for this array is contained within these shrouds. And then they're connected to the side at the end, and then they're sent in the building for inversion to AC so that they're usable inside the building. The total size of this solar array is 55 kilowatts. I typically refer to this as enough to power 8 to 10 energy efficient American homes. And it was installed approximately 8 years ago, and it's still performing pretty well at approximately the 95% of its original capacity. We do see degradation over time. The sun degrades all materials, and however, during the first 10 to 15 years of a solar panel's life, we see very minimal degradation. And we've actually seen this one perform pretty well. Because it's such a thin film, and because it was in the initial, because it was a Generation 1 installation, this technology is only in the 12 to 12.5% efficiency range, wherein other solar panels, such as the one that are on my roof of my home, they're 21% efficient. So in the same footprint, we're actually generating less electricity and these were more expensive. They were in the range of $5 per watt installation, wherein at home I paid $3.35. I think that's now down to about $2 per watt. But as we see economies of scale rise and the prices go down, technologies such as this have gotten up into the 16 to 17% efficiency range, and it's good for an installation on something such as a standing seam metal roof, where each of these sections will fit between the vertical pylons.